Hi everyone. In this lecture, we will do the complete analysis of this lattice, this divisibility relation where base set is Dn. So what is Dn? First of all, let's understand what is Dn. So if n is a natural number, means n is a positive integer, then what is Dn? Dn is basically set of all divisors of n. Okay, set of all divisors of n. This is your Dn. Now let's see. For example, if I ask you, let's assume that you have a set of natural number. Let's assume n is 4. Then what will be Dn? Dn will be set of all divisors of n. Set of all divisors of n. So I can say set of all divisors of 4. That is basically 1 to 4. Okay. This will be the Dn. So for example, if I give you n equal to 5, then what will be D5? D5 will be basically set of all divisors of 5. That will be 1 comma 5. If I give you n equal to 6, then what will be d6? D6 will be set of all divisors of 6. That will be 1 2 3 6. Okay, so this is the idea. So this is the definition. For example, if I ask you what is what is d20, so very easily you can understand. First of all, what you do, you write the factorization of prime factorization of 20. So what is 20? 20 is basically, I can say, 2 square multiplied by 5. This is the prime factorization of 20. Now what are the divisors of 20? So I can say 1 is the divisor of 20, 2 is the divisor of 20, okay, 4 is the divisor of 20, 5 is the divisor of 20, 10 is the divisor of 20, and 20 is the divisor of 20. So this is the idea. Okay, so this is the concept of Dn. So first of all, you understand what is Dn. Remember, Dn is a set of all integers, set of all divisors of n. Okay, so for example, this is d6, this is d5, this is d20. And similarly, if I ask you, for example, what is d32? Remember what is 32? 32 is basically 2 power 5. Okay, this is the prime factorization of 32. So all the divisors of 32, that is 2, 1, 2, 4, 8, 16, 32. This is the d32. So this set is d32 because this is the set of all divisors of 32. Now once this Dn is clear, now let's analyze this relation. Okay, let's analyze this poset Dn comma divisibility. So this is our divisibility relation. In the last video we have already seen what is divisibility relation. So this is the divisibility relation. Okay, and the base set is Dn. This is the base set, means base set is a set of all divisors of n. Now let's see the properties of this. So you already know that this is a poset because definitely all these properties are satisfied. It is reflexive because a always divides a. Divisibility relation is reflexive. This is antisymmetric also because what is n? N is a natural number. Remember this n, this is basically a natural number. This is a positive integer. Okay, so Dn is basically set of all divisors, set of all positive divisors of n. So I can say that this is set of all positive divisors. Okay, I don't have to write it because by default we basically want to say that we are talking about divisors, positive divisors. Okay, so Dn is set of all positive divisors of n. Okay, now so this is a reflexive, this is antisymmetric, and this is a transitive. So I can say that this Dn comma divisibility, this is definitely a poset for all n. Whatever n you take, whatever natural number n you take, okay, this Dn comma divisibility, this is definitely a poset. Okay, now let's analyze whether it will be a lattice or not. So when can I say this will be a lattice? So just think about it. Okay, so before that, let's take one example. For example, if I give you d4, what is d4? D4 is 1 2 4. Okay, so this is d4 divisibility relation. Okay, so what will be the hash diagram? Hash diagram will be 1 divides 2, 2 divides 4. This will be the hash diagram. So clearly this is not Boolean algebra. This is a lattice. Yes, this is a lattice. Definitely this is a lattice. Okay, but uh, what can you say about other things? For example, can I say complemented? This is not complemented lattice. This is a total order. So this is a total order. I can say this is a total order set. This is a toset, and every toset is lattice. Every toset is lattice because for any two elements you have GLB LUB. For example, if I ask you what is GLB of what is LUB of 2 or 2 comma 4, that will be 4. What is GLB of 2 comma 4, that will be 2. What is LUB of 1 comma 4, that will be 4. What is GLB of 1 comma 4, that will be 1. Okay, so for every two elements, any two elements you take, for every two elements what we have GLB LUB. So every total order is always a lattice. So this is a lattice. Is this complemented lattice? This is not complemented lattice because you can notice complement of 2 does not exist. There is no complement of 2. And is this distributive? Yes, total order set, this is always distributive. Why this is distributive? Because you can notice in this is a chain, and in this chain you cannot have a sublattice which is kite or pentagon. So this is definitely distributive, but this is not complemented. And yes, this is the greatest element and this is the least element. So this is bounded. So this is the analysis of this poset. Now let's see another. For example, if I ask you what is a d12 comma divides. Okay, so first of all, what is d12? So what you do when you want to find d12, first you write the prime factorization of 12. What that will be? That will be 2 square into 3. This is the prime factorization of 12. So what are the divisors of 12? That will be 1 2 3 4, okay, 6 and 12. These are the divisors of 12. Now make the hash diagram. So you can notice 1 is the least element because 1 divides everything. Okay, so 1 is the least element. I can say 1 divides 2, 1 divides 3, and 2 divides 4, and 2 comma 3 they divide 6, and okay, 4 comma 6 they divide 12. So this is the hash diagram. In this hash diagram, least element is always 1 because 1 divides everything, you can notice. And the greatest element is 12. Why this is the greatest element? Because remember, in this set everything is a divisor of 12. So everything will divide 12. Okay, so this is the greatest element because in this set every element is this is the divisor of 12. Basically these are the divisors of 12. So every element is divisor of 12. Every element will divide 12. Okay, so I can say 12 is the greatest element, this is the least element. Now, okay, is this a lattice? Yes, this is a lattice. You can clearly see this is a lattice. Why this is a lattice? Because just check LUB GLB. For any two elements, you can find the LUB GLB. So, for example, what is the LUB of 2, 3? Remember, in this lattice, LUB of 2, 3, that will be 6. You can notice this is 2, this is 3. So, the LUB will be 6. And what is the GLB of 2, 3? That will be 1. Any two elements you take, you can find their LUB GLB. For example, what is the LUB of 3, 4? The LUB of 3, 4, that will be 12. This is 4, this is 3. So if you find the LUB, then LUB will be the 12. Okay, and what is the GLB of 3, 4? That will be 1. Okay, so similarly, if I ask you, for example, what is the LUB of 2, 6? The LUB will be 6. And what is the GLB of 2, 6? That will be 2. Okay, so one thing you can notice here, what is that? In this lattice, okay, so these are some points that we should notice, that in this lattice dn divisibility, okay, divisors of n. So first of all, yes, this is a poset. This is the first thing to note, that this is a poset. The second thing you can notice, yes, this is a poset. Remember, the base set should be dn. Dn means divisors of n. Okay, so this is a poset. The second property is, what is the least element? You can notice that in this dn, 1 always will be there. 1 always belongs to dn, and 1 will be the least element because 1 divides everything. 1 divides a for all a in dn. Okay, 1 will always divide. So 1 divides a for all a in dn. So I can say 1 is the least element. And what is the greatest element? What is the greatest element in this? Greatest element will be n, because remember, in this every element is divisor of n. In this every element is divisor of n. So for all elements in dn, every element in this dn, I can say that is divisor of n. It means a divides n. So this is the definition of greatest element. So I can say that n is the greatest element. And another thing is that this is a lattice. Yes, this is a poset. This is a lattice. Why this is a lattice? Because for every two elements we have GLB, LUB. Okay, this is a lattice. Why? Because if you take any two elements, if you take any two divisors of n, if you take, then what will be their LUB? You can notice LUB will be the LCM and GLB will be the GCD. Okay, so this is what you can notice. Very simple point. So I can say, for example, here you can notice, in this you can clearly see that LUB of any two elements, if you know. Okay, so what is the LUB of any two elements? For example, if I ask you what is the LUB of 4, 6, that will be the LCM of 4, 6. And what is the LCM of 4, 6? That is 12. And if I ask you what is the GLB of 4, 6, that will be GCD of 4, 6. And GCD of 4, 6 is basically 2. So this is the idea. So in this poset, this is a lattice. Why? Because for every two elements we have LUB. LUB is the LCM, and for every two elements we have GLB, which is the GCD. You can take, for example, let me take this D18 comma divides. Okay, so let's analyze this. First, what you do, you write the prime factorization of 18. What is that? that is 3 square into 2. This is the prime factorization of 18. So what is D18? D18 will be, that will be 1, 2, 3, okay, 6, 9, 18. This will be the D18. D18 is the set of all divisors of 18. So these are the divisors of 18. Now make the hash diagram. Remember, 1 is the least element because 1 divides everything. So 1 divides 2, 1 divides 3, and you can notice 2 divides 6, 3 divides 6, and this 3 divides 9, and finally I can say that this 18. Okay, so 6 divides 18 and 9 divides 18. So you can clearly see the greatest element. If you notice, this is the greatest element and this is the least element, because in this set every element will divide a. I can say for all a in this D18, I can say that a divides 18. Every element here will divide 18. So I can say that this 18 is the greatest element. So the greatest, if you find, the greatest element is 18. And what is the least element? 1 divides everything, so least element is 1. And you can notice, yes, this is a poset. You already know this is a poset. This is the hash diagram. But is this a lattice? Yes, this is a lattice because for every two elements we have GLB, LUB. For example, if I ask you what is the LUB of 2, 9, what is the LUB? LUB will be the LCM. LUB will be the LCM. So LCM of 2, 9, that will be 18. And if I ask you what is GCD of 2, 9, that will be the, that, sorry, GLB of 2, 9, that will be the GCD. That will be the GCD of 2, 9, and GCD of 2, 9 is basically 1. You can see from this hash diagram. In this hash diagram, what is 2 or 9? LUB of 2, 9, that will be 18, and GLB of 2, 9, that will be 1. So this is the idea. Okay, so similarly in this D18 divisibility, if I ask you, for example, what is 2 or okay, so what is 2 or 6? So what that will be? That will be LCM of 2, 6. That will be LCM of 2, 6, and LCM of 2, 6 is 6. And what is 2 and 6? Means GLB. What is GLB? GLB is the GCD. GCD means greatest common factor. So what is the greatest common factor of 2, 6? That is 2. You can notice that actually why this is happening. This is happening because in this in this 2 is related to 6, because 2 divides 6, and whenever 2 is related to 6, then automatically what it means, it means 2 LUB of 2, 6 will be 6, and GLB of 2, 6 will be 2. Okay, so this is the idea. So what is the GLB? GLB will be the GCD and LUB will be the LCM. So this is a lattice. This DN divisibility, this is always a lattice. Okay, and the LCM will be in this divisibility relation, in this DN divides, in this, remember in this LUB of A B, if I ask LUB of A B, means if I ask A or B, then that will be the LCM of A B. Okay, and if I ask you what is GLB of A B, what is GLB of A B, means if I ask you A and B, then that will be the GCD of A B, greatest common divisor of A B. Okay, so this is the idea. So this is a lattice because for every two elements, we have LUB, we have GLB. So this is definitely a lattice. Now let's analyze some more properties, whether it is distributive or not. Okay, whether it is complemented or not, whether it is bounded or not. So all these properties. So first of all, it is bounded, right? Dn this Dn divisibility, this is definitely a bounded lattice. Why this is a bounded lattice? Just check it. This is a bounded lattice because the greatest element. Why this is a bounded lattice? Because the greatest element is n, and the least element is 1. So this is a bounded lattice. What about distributive? What can you say about distributive? So this is the question. Can I say that this Dn divisibility, can I say this is distributive? Can I say this is distributive? Just think about it. Can I say this is distributive, Dn divisibility? The answer is yes. Okay, is this distributive? The answer is yes. Why this is distributive? Because remember in this Dn divisibility, you can notice that your GLB is same as GCD. Okay, your GLB is same as GCD, and your LUB is same as LCM. Okay, so the distributive property is satisfied. Why? Because in number theory, this is a fact. In number theory, okay, this is a fact from number theory. So this is don't worry about the proof, because proof is not required for us. This is a fact from number theory. Okay, so in number theory, this is the fact that GCD and LCM, they distribute over each other. Okay, so this GCD and LCM, they distribute over each other. Okay, so the proof is not required for us. Okay, you can skip because this is not a part of discrete mathematics. This is basically part of number theory, so we don't worry about it. Okay, but this statement is very important for us. So GCD and LCM, they distribute over each other. Okay, so GCD comma LCM, they distribute over each other, and you can notice that in this dn comma divisibility, in this dn comma divisibility, you already know that your GLB is the same as GCD and your LUB is same as LCM, and we already know that GCD comma LCM, they distribute over each other. They satisfy the distributive property. They satisfy the distributive property. Okay, they satisfy distributive property. What I want to say, I want to say that so basically, okay, GCD comma LCM, they satisfy the distributive property. What it means, it means that if I ask you A and B or C, remember this is LCM, and remember this is GCD, because in this, because you know that in this poset GCD GLB is the GCD and LUB is the LCM. So this GLB is the GCD and this LUB is the LCM. Okay, and remember GCD comma LCM, they distribute over each other. This we know from number theory. So finally I can say, because they distribute over each other, so I can say this will be equal to A GLB, A and B, or A and C. Okay, so this is the idea. And remember, this is OR, this is LUB is the LCM, and this is your GCD. So this is the idea. So I can say this is a distributive. So finally, because of this, I can say that dn comma divisibility, this is a distributive lattice. This lattice is a distributive lattice. This lattice is definitely distributive. Okay, now the next question that we should ask is, can I say dn comma divisibility is complemented lattice? So remember, this is distributive, this is bounded, this is lattice, GCD, GLB is the GCD, LUB is the LCM, all these things we have seen. So this is a distributive lattice, there is no problem. Okay, this is bounded lattice, everything we have seen. But now the question is this complemented lattice? Is this dn comma divisibility, is this complemented lattice? Let's take some examples. With examples, this concept will be clear. So let's assume that you have D4. What is D4? Remember, D4 is 1 to 4. Okay, so now think about it. Is this complemented? Remember, this is a total order. If you notice, this is a total order. This is actually a total order. So if you make the hash diagram, then 1 divides 2 and 2 divides 4. And you can notice, yes, this is distributive. Yes, this is distributive. Dn comma divisibility, this is distributive, but this is not complemented. This is not complemented. Why? Because 2 inverse does not exist. There is no complement of 2. The complement of 2 does not exist. So this lattice, this D4 is definitely not, I can say this D4 is definitely not complemented lattice. This is definitely not complemented lattice. Now let's see another one. What about D6? Okay, what about D6? Remember, the D6 is basically 1, 2, 3, 6. This is your D6. Is this complemented? So what is the hash diagram for D6? The relation is divisibility. The relation is divisibility. So I can say 1 is the least element, 1 divides 2, 1 divides 3, and 2 comma 3, they divide 6. You already know this is a square structure. Remember, this is a square structure. This square structure is actually Boolean lattice. So because this is Boolean lattice, so this is complemented also, and this is distributive also, bounded also. So this is Boolean lattice, and you can clearly see every Boolean lattice is complemented. So this is actually complemented. Why this is complemented? Because for every element we have complement. You can clearly see what is the complement of 1, that will be 6. Complement of 6, that will be 1. Okay, complement of 2, that will be 3, and complement of 3, that will be 2. So for every element we have complement. So I can say yes, this is complemented lattice, and this is always distributive. This dn, this d6, okay, this dn is always always distributive. So you can clearly see d4 is not complemented, but d6 is complemented. Now similarly, if I ask you, what about d5? What about this d5? Remember, d5 is 1 comma 5. Okay, so what about this? The hash diagram will be 1 divides 5. The relation is divisibility. Remember, the relation is same divisibility. Now this is also Boolean lattice. We already know this is also Boolean lattice. Because this is Boolean lattice, so this is also complemented. This is also complemented lattice. This lattice is also complemented lattice. Why? Because every element has complement, every element has at least one complement. 5 complement is 1. So I can say that D5. Okay, so what can I say? I can say that this is not complemented. This is not a complemented lattice, but D5 comma D6, these are complemented lattice. Similarly, you can check D7 is also complemented lattice. What about D8? Let's check D8. D8 is not complemented lattice. Okay, let's check about D8. So if you check for D7, remember D7 is 1 comma 7. So if you check for D7, this will be your D7. Now let's check for D8. What will be D8? D8 is basically, remember, 8 is basically 2 power 3. So what will be D8? D8 is the set of all divisors of 8. So that will be 1, 2, 4, 8. And the hash diagram will be 1, 2, 1 divides 2, 2 divides 4, 4 divides 8. So here you can clearly see that this is not complemented. Any total order with more than 2 elements is not complemented. So I can say this is not, is this complemented? Is this complemented? The answer is no. This is not complemented. Okay, because the complement of 2 does not exist, and also complement of 4 does not exist. So this D8 is also not complemented. So you can clearly see the question is, can I say Dn is complemented? But you can notice that some of them are complemented, some of them are not complemented. Okay, so this is the question. If I ask you Dn comma divides, is this complemented? So this may or may not be complemented. This may or may not be complemented. This may or may not be complemented. Sometimes it is complemented, sometimes it is not complemented. So whether it is complemented or not, that will depend on n. So I can say it will actually depend on n. It will depend on n. Depending on the n, this will be either complemented or this will be not complemented. Now let's see for which n this will be complemented. Okay, this is a nice this is a nice question to think about. For which n? So this is the question. I can say for which n, for which n, okay, this dn comma divisibility is complemented lattice. For which n can I say that this is a complemented lattice? For which value of n? Okay, now let's think about it. So let me tell you that, see, okay, if you want to see this, for which value of n this is complemented lattice, so the answer is, okay, here let me tell you the answer. The answer is n should be square free. Okay, n should be square free. N should be square free. What I want to say is square free. N should be square free. See, if you look at this, for example, if you look at 8, then there is 2 power 3. This is not square free. This 8 is not square free, because I can say that 8 is, if you see the prime factorization, in the prime factorization I can say this is not square free. I can say this is 2 square into 2. So this is not square free. Okay, so this 8, this is not square free. I can say this is not square free. Or I can say, why, what is the definition of square free? Square free means, square free means it is not divisible by square. Okay, square free, square free, what can I say? N is square free. N is square free if and only if n is not divisible. N is not divisible. N is not divisible by p square, where p is some prime, where p is some prime number, where p is a prime number. Okay, so then we call it square free. So this is the definition of square free. Square free means a number is square free if it is not divisible, if it is not divisible by p square, where p is a prime number. You can notice 8 is divisible by 2 square. 8 is divisible by 2 square. 2 is prime number. 8 is divisible by 2 square. So I can say 8 is not square free. Because 8 is not square free, you can notice this d8 comma this is not complemented. You can notice this is not complemented. Now let's see another example. For example, look at 6. What is the prime factorization of 6? That is 2 into 3. This 6 is square free. This is a square free. This is square free because this 6 is not divisible by p square, where p is prime number. So I can say this 6 is no, okay, there is basically, this is square free. What it means? It means there is no prime number. There is no prime number. There is no prime number p such that p square divides 6. So I can say this 6 is square free, and because this is square free, so you can notice this d6 comma divisibility is complemented lattice. This is a complemented lattice. Okay, so I'm just telling you what is a square free number, and this 6 is a square free number. Now what about, for example, what about 10? 10 is also a square free number. This is the prime factorization of 10, and this is also a square free number. Now let me tell you another way to check whether a number is square free or not. Okay, the square free number basically has this type of structure. The prime factorization of square free number. Let's look at that. So let's look at the prime factorization of square free number. Remember the definition of square free number. A square free number is a number which is not divisible by p square, where p is a prime number. Basically, see, this 6 is square free. Why? This 6 is square free because there is no prime number such that p square divides 6. There is no prime number such that p square divides 6. Square free means n is square free if and only if it is not divisible by p square, where p is a prime number. Now, what is the prime factorization of square free number? See, okay, just look at this. Can I, okay, is it possible that a square free number, for example, let's assume, is this a square free number? If the prime factorization is like this, is this a square free number? Okay, so what is this number? This number is basically your, this number is 150. So you can check, is this square free? This is not square free because of this situation. So because of this, I can say that this is not square free. This is not square free. Why this is not square free? Because you can clearly see that 5 square will divide, I can say 5 square divides 150. So because 5 square divides 150, and remember 5 is a prime number, because 5 square divides 150, so I can say this, okay, so I can say that this is not square free. So what is the prime factorization will look like for a square free number? The prime factorization will look something like this. If n is a square free number, if this n is a square free number, then the prime factorization will be like this. The power will always be 1. The power of every prime number will always be 1. The power of every prime number in the prime factorization. In the prime factorization, the power of every prime number will always be 1. This is the definition of square free. So for example, this 2 multiplied by 7 multiplied by 11. Okay, this number is definitely square free. Okay, so what is this number? I think this number is, okay, 144. So this number, so this is actually 154. Okay, this number you can clearly see this is square free because in the, this is the prime factorization. In the prime factorization, all the powers are 1. So this number is square free. This number is square free. What about this number? For example, if I give you 2 power 4 multiplied by 3 power 5, this number, okay, whatever is this number is not square free. I can say this number n, this is not square free. This number is not square free. Why this is not square free? Because you can notice in the prime factorization, powers are other than 1. Remember, for a square free number, the powers in the prime factorization will always be 1. Okay, but you can notice this is not a square free number. Why this is not square free? This is not square free. Why? Because you can clearly see that, okay, you can clearly see that this 3 square will divide it, right? 3 square divides n. Okay, 3 square will divide n. So I can say this is not square free. Whatever is this number is not square free. Okay, so this is the final definition. Remember, these are the definitions of square free number. When can you say that you have a square free number? When can I say that you have a square free number? When can I say square free number n? So n is square free. When can I say square free number n? If n is, okay, there are two definitions. You can use any of them. The definition number 1 is, okay, n is not, there is no prime number. Okay, there is no prime number. There is no prime p such that p square divides n. There is no such prime number. There is no prime p such that p square divides n. This is the definition of square free number. Or you can use this definition. In the prime factorization of n should be like this. Okay, so the prime when you do the prime factorization of n, okay, now when you do the prime factorization of n, then what should happen? For every prime number, the power must be 1. For every prime number, the power must be 1. Okay, for every prime number, the power must be 1. So this is important. The power must be 1. This should be the prime factorization of n. Then we will say that this is a square free number. So this is the definition of a square free number. Now I am saying that, okay, now this is the note. What is the note? That this dn comma divisibility, this is complemented, this is complemented if and only if, this is complemented if and only if n is square free. If and only if n is square free, means if n is square free, then this will be complemented, and if it is complemented, then n will be square free. Okay, so for example, if I ask you, okay, tell me which of them is complemented. If I ask you, for example, what about d21? What about d21? Is this complemented? Is this lattice complemented? Very simple. Just look at 21. What is 21? 21 is basically, I can say, okay, that is a 7 multiplied by 3. Yes, this is a square free number, because in the prime factorization all the powers are 1. Okay, so this is a square free number, so this n is square free, so I can say yes, this is complemented. Yes, this is complemented, and you can check it. Why this is complemented, you can check, because what is d21? D21 is basically 1, 3, 7, 21. These are the divisors of 21. Now, what will be the hash diagram? Hash diagram will be 1 divides 3, 1 divides 7, and 3 comma 7. They divide 21. And you remember that this is a Boolean lattice. You already know that this is a Boolean lattice. This is a Boolean lattice. So this is a complemented lattice. Here you can notice that the complement of 3 will be 7, and the complement of 7 will be 3. The complement of 1 will be 21, and the complement of 21 will be 1. Okay, so this is the idea. So this is a square free. This is complemented because 21 is square free. What about 34? What about this 34 divisibility? So first of all, you find the prime factorization of 34. What that will be? Prime factorization of 34, that will be 17 into 2. This is the prime factorization. You can notice all the powers are 1, so this is also square free. I can say this is also square free, so this is complemented. So this lattice is complemented because n is square free, so this is complemented. You can check it out. What is d34? What is d34? D34 is basically 1 1 to 17 34. This is d34. Okay, and the hash diagram will look like this. This is the hash diagram, so you can clearly see this is a Boolean lattice. So this is always distributive. I told you dn comma divisibility, for every n this is distributive, but you can notice because 34 is square free, so I can say this is a complemented also. Okay, now what about this number? If I ask you, what about d50? What about d50? Is this complemented? First, you write the prime factorization of 50. The prime factorization of 50 is basically this. Now you can clearly see, because of this I can say that this is not square free. This is not square free. Why? Because in the prime factorization, some prime number has power more than 1. You can notice the power is more than 1. So I can say this is not square free. Or I can say that 5 is square. Remember, 5 is a prime number. Remember, 5 is a prime number. So this 5 is a prime number, and you can clearly see that this 5 is square. This 5 square divides 50. So I can say this is not square free. So this 50 is not square free. So this is not square free. And because this is not square free, so this is not complemented. This lattice is not complemented. This lattice is not complemented. You can clearly see why this is not complemented. Just write down what is d50. D50 will be 1, 2, okay, and then it will be 5, 10, 25, and 50. This will be the D50. Now, if you make the hash diagram for D50, what that will be? Hash diagram will be 1 divides everything. 1 divides 2, 1 divides 5, and then you can notice that, okay, so this 2 divides 10, and there is 25, so 5 divides 25, and there is 50. Okay, so everyone will divide 50 because in D50 everything is a divisor of 50. So here you can clearly see that this is not complemented. Here, what this is not complemented. Why this is not complemented? This is not complemented because just see what is the complement of 10. The complement of 10 does not exist. There is no element which is complement of 10. The complement of 10 cannot be 25 because you can notice the GCD of okay, see, 10 complement is not 25. Why? What is the reason? Because if you find the GLB of 10 comma 25, that will be the GCD. I told you that will be the GCD of 10 comma 25, and the GCD of 10 comma 25 is 5, which is not equal to the least element. So the For 10 comma 25, the GLB will not be a list element. Okay, so that's the reason I can say 10 inverse, 10 complement does not exist. Similarly, I can say 5 complement also does not exist. Okay, but yes, 2 complement is there. 2 complement is 25, 25 complement is 2. Okay, 1 complement is 50, and 50 complement is 1. But there is no complement for 10, there is no complement for 5. So this is not a complemented lattice. Okay, so I hope the idea is clear. So a lattice, this dn comma divisibility, this is complemented if and only if n is square free. This is the idea. Let's see the conclusion, final conclusion. So let's see the conclusion of this is your dn comma divisibility. Okay, here remember what is this dn. First of all, you understand this dn. This dn is basically the set of all divisors of n. Remember, this is set of all divisors of n. This is set of all divisors of n, where n is some natural number. Okay, so for example, if I ask you what is d1, d1 is simply 1. If I ask you what is d2, d2 is 1 comma 2. If I ask you d3, d3 is 1 comma 3. Okay, if I ask you d4, d4 is 1 comma 2 comma 4. Okay, so similarly, if I ask you for example d14, d14 is 1 comma 2 comma 7 comma 14. Okay, so this is the idea. So dn is what? Dn is a set of all divisors of n. This is your dn, set of all divisors of n. Okay, and now let's see the points. So this dn comma divisibility, first of all, this is always a poset. This is always a poset for all n. Okay, this is always a poset. Second, this is a lattice. This is a lattice. Okay, third point, here the GLB, if you want to find GLB of two elements, okay, so if you want to find GLB, then GLB is same as GCD. Here GLB is same as GCD, and here LUB is same as LCM. So GLB is same as GCD, LUB is same as LCM. So for example, if you want to find out A or B, that means LUB, you want to find LUB of A comma B, then that is same as LCM of A comma B. Okay, so this is the idea. And similarly, if you want to find out GCD, if you want to find GLB of A comma B, A and B, means you want to find out GLB of A comma B, then that is same as GCD of A comma B. Okay, so this is the idea. So this is a poset, this is a lattice, GLB, GCD, LUB is LCM, all these things we have seen. Okay, these are important. Now the next thing, dn comma divisibility, this is always a distributive lattice. This is definitely a distributive lattice. This is a distributive lattice. Why this is distributive lattice? Because I told you that LCM comma GCD, they distribute over each other. Okay, because LCM comma GCD, they distribute over each other. So this is this is always a distributive lattice. And what is the next thing? What is the least element? The least element is 1, because 1 will divide anything. And what is the greatest element? Greatest element is n. So finally I can say that this is always a bounded lattice. This is definitely a bounded lattice. This is definitely, and the greatest element is n, and the least element is 1. And the last point, okay, dn comma divisibility, the sixth point that we have is, this is complemented if and only if. Okay, so this is complemented if and only if n is square free. If and only if n is square free. So if and only if n is square free, then this is complemented. Okay, and you can notice that, remember, okay, the next point I can say, this is Boolean algebra. When can I say this is Boolean algebra? Boolean algebra or Boolean lattice. When can I say this is Boolean lattice or Boolean algebra? Both are same. Boolean algebra, another name is Boolean lattice. So when can I say this is Boolean algebra or Boolean lattice? If and only if n is square free. If and only if n is square free. Because remember, when n is square free, Boolean lattice means complemented distributive. This is always distributive. This is always distributive. But this is complement only if and only if as n is square free. So I can say this will be Boolean algebra if and only if n is square free. Okay, so if n is square free, then this will be a Boolean algebra. If n is not square free, this will not be a Boolean algebra. Okay, and the next point, the eighth point. See, if your n is like this, okay, in this dn comma, divisibility, okay, let me tell you that if your n is like this, Okay, so basically complements. This is the last point about complements. Okay, let's see what are the complements of the elements. Complements of elements of Dn. Okay, so let's find out complements of elements of Dn. So remember, for example, if your n is like this, if this number n is like this, like p1 multiplied by p1 power x1, okay. So if your let me tell you, like, okay, if this is p1 multiplied by p2 multiplied by and so on pm, so if all the powers are 1, then in this case, because n is square free, in this case n is square free, and in this case what will happen, everything will have complement, every number will have complement. So in this situation, when n is like this, n is p, okay, the prime factorization of n is like this, p1 multiplied by p2 multiplied by p3 and so on multiplied by pm. Okay, so let me just take p4. Okay, so let me take like this. So if your n is like this, then what is the complement of p1? The complement of p1 will be the remaining thing. Okay, so the complement of p1 will be the remaining thing, means p2 multiplied by p3 multiplied by p4. So basically what I want to say, complement of p1 will be n divided by p1. Similarly, if I ask you complement of p2, that will be n divided by p2. Okay. Similarly, if I ask you complement of P2 and P2 multiplied by P3, if I ask you complement of this, then that will be n multiplied n divided by P2 multiplied by P3. Okay, so this is the idea. If I ask you complement of P1, P2, P3, if I ask you complement of P1, P2, P3, this multiplication complement, then that will be n divided by P1, P2, P3. Okay, so that is the idea. Okay, so one example, with example this will be clear. So if your number is like this, let's assume your number is 5 multiplied by 7 multiplied by 19. Now this is the prime factorization, all the powers are 1. Okay, so in this situation, okay, also let me take maybe I can take you can take 23. Okay, so all the powers are 1. So this is your number n. Now because this is square free, you can clearly see this number is square free. So I can say, because this is square free, so I can say this dn comma divisibility, this is a boolean lattice, I can say this is complemented, means every element will have, this is a complemented lattice, every element will have complement. Now if I ask you what is the complement of 5 in this, then that will be simply n divided by 5. Okay, and if I ask you what is the complement of 5 multiplied by 19, that will be n divided by 5 multiplied by 19. Okay, and if I ask you complement of for example, if I ask you complement of 5 multiplied by 7 multiplied by 23, if I ask you complement of this, then that will be n divided by 5 multiplied by 7 multiplied by 23. Okay, so this is the idea. Okay, and the complement of this whole thing, complement of n, if I ask you, if I ask you complement of n, that will be n divided by n, and complement of 1 will be, okay, n divided by 1. So this is the idea. So when n is square free, so this is the result, I can say this is the result. Okay, this is the result. When n is square free, when n is square free, when n is square free, then okay, then this dn comma this divisibility is, this is what, this is complemented lattice. You already know this is complemented lattice. Okay, and and for all a, okay, for all a which are in dn, okay, which are in this, which are in this base set. So for, if n is square free, then for all a which are in this, what will be the complement of a? The complement of a will be n divided by a. Okay, so for example, what will be complement of 1? That will be n divided by 1, means complement of 1 will be n. For example, what will be complement of n? That will be n divided by n, that will be 1. Okay, so this is the idea. So okay, so so for all, okay. So for all elements, if n is square free, then for all elements the complement will be basically n divided by a. This will be the complement. When n is not square free, then what will happen? I can say when n is not square free, when n is not square free, then some elements don't have complement. Then okay, then in dn comma divisibility, in this lattice, in this lattice, in this lattice, some elements do not have complement. I can say some elements do not have complement. Okay, some elements do not have complement. So in this situation some elements do not have complement. Okay, which elements do not have complement? Let's find it out. So with example you can just check it out. Let me if you were, for example, if you have 2 power 2 into 3 power 3, if this is your number, so the number is 108. Okay, now you can clearly see this is not square free, this is not square free, this is not square free. Here you can clearly see, let me tell you that this 2 will not have, see, okay, this 2 will not have complement, because you can notice the complement of 2, what that should be. Actually if you notice, complement of 2 should be, the ideal complement of 2, that will be 108 divided by 2. And what is that? That is basically 54. But this is not complement of 2. This is not complement of 2. Why this is wrong? Why this is wrong? Because if you notice, LCM of 2 comma 54 is 54. That is not same as greatest element. Okay, so LCM of 2 comma 54 is 54. That is not greatest element. So 2 inverse is not 54. So I can say 2 inverse does not exist. So in this I can say that 2 inverse does not exist. 2 inverse does not exist. But 2, okay, remember, for this complement will exist. For this means if I ask you 2 square complement, that will be n divided by 2 square, means that will be 3 power cube. Okay, so because you can notice, let me tell you why. Because if you notice 2 square complement, that will be 108 divided by 2 square, that will be 3 power 3. Because if you notice, if you find out LCM of 4 comma 27, then that will be actually 108, and the GCD of 4 comma 27, that will be 1. So that is the reason I can say that complement of 4 will be there, but complement of 2 will not be there. Similarly complement of 3 will not be there. Okay, in this 108, which is 2 square into 3 cube, here let me tell you, complement of 3 does not exist. Why complement of 3 does not exist? Because what should be the complement of 3? The complement of 3 should be this, correct? The complement of 3 should be this. And what is that? That is 36. That is 36. But you can notice what is the problem. The problem is LCM of 3 comma 36 is 36, which is not greatest element. So I can say that 3 complement is not equal to 36. Okay, so I can say 3 complement does not exist. So I can say 3 complement does not exist. Remember, 3 complement does not exist. 3 complement does not exist. But 3, okay, for this whole thing there will be complement. If I ask you the complement of this whole thing, that will be 108 divided by 3 power 3, means 2 power 2. But the complement of 3 power 2 does not exist. Okay, the complement of this does not exist. So for this complete thing there will be complement. So what I want to say, if your number is like this, means p1 power, let's assume p1 power 4 multiplied by p2 power 2 multiplied by p3 power a 6. Okay, then in this situation, let me tell you, for this whole thing there will be complement. So for this whole thing there will be complement, and that will be this. For this whole thing there will be complement, that will be this. But there will not be a complement for p1. P1 complement does not exist. P1 square complement does not exist. P1 cube complement does not exist. Okay, so for this whole thing there will be complement, but there is no complement for p1, there is no complement for p1 square, there is no complement for p1 cube. Similarly there is complement for this whole thing. Okay, so if you want to find the complement of p2 square, for this p2 square there is a complement, that is n divided by p2 square, that is n divided by p2 square. But there is no complement for p2. If I ask you what is the complement of p2, that does not exist. So this is the simple idea. For example, if you have 2 power 3, okay, if you have this number 2 power 3, then in this situation let me tell you that for this 2 power 3, for this complete thing there will be complement. For this complete thing means okay, for 8 that will be complement, that will be 8 divided by 8, that will be 1. But there is no complement for 2. There is no complement for 2. There is no complement for 2 square. There is no complement for 2 square. And also there is no complement for, there is no complement for 2. There is no complement for 2 square. But for this complete thing, there will be complement. Okay, so this is the complete summary. Okay, I hope this every point that we have seen, I hope that is clear. So when n is square free, then for any element you can very easily find the complement that will be n divided by a. But when n is not square free, when n is not square free, then some elements do not have complement. Okay, some elements are not going to have complement. Okay, those elements which have complement, for them complement will be n divided by a. Okay, so those elements, I can say that those elements which have complement, those elements which have complement, okay, those elements which have complement, for them what will happen, for them complement of a will be basically n by a. But some elements may not have complement, but those elements which have complement, for them the complement will be n divided by a. Okay, so for example, you can notice here the complement of 3 square does not exist. The complement of 3 cube will be there, but the complement of 3 square is not there. The complement of 3 is not there. Okay, so this is the complete idea. Okay, if anyone has any doubt, you can ask in the comments. So let me tell you, the complete analysis we have seen